Okay, it's page 7 now of this lecture in week 8, equations and formula. We're still looking at formula. We're looking at Pythagoras' theorem, and that's written as a formula, and you've probably heard of it. It's c squared equals a squared plus b squared. It refers to right-angled triangles, so triangles that have a 90-degree angle in them. That's one there. That little square indicates that that angle is 90 degrees. You'll notice in those triangles the longest side of the triangle is the one opposite the right angle. It's known as the hypotenuse. Okay. Now, we're asked to label the vertices and the sides of the triangle. Well, there's generally a convention for labeling triangles. We label the right angle as C, and the other sides can be AB. Okay. Then we have, and notice they're capitals, so they're the vertices. Then we call the side opposite the right angle, the hypotenuse, little c. The side opposite A, little a. And we're referring to its length here. So little a is the length of the side opposite the vertice big A. And of course this side opposite the vertice that's labelled capital B has length little b. So that's the convention for labelling a right-angled triangle. Now, Pythagoras' theorem says that the square of the hypotenuse of a right-angled triangle is equal to the sum of the squares of the other two sides. So this is taking the words that define the formula, and we've got to actually now turn them into an equation or a formula using the symbols that we've been given. Now, the square on the hypotenuse. Okay, now have a think about this. We've got a length of 5 centimetres there on that side. So if I divide that up into 5 centimetres along the hypotenuse, and they're not very straight lines, are they? And because it's a square on that side, we've got another 5 centimetres there. So the square on the hypotenuse is 5 times 5, that's 5 squared. And we said that c is 5, so it's c squared. And the same thing happens on the other sides. We look at the squares on the other side. There's the side that's a squared, and it's the sum of the squares, so a squared plus b squared. So we have 25 squares on the hypotenuse. Let's have a look at the sum of the squares on the other two sides. So side A, we're splitting that into lots of 4, so each one of them is a centimetre, and we know that A is equal to 4 centimetres. We've got that information back up here. So there we have 16 squares there. Now let's have a look at the last one, which is this one. 3 centimetres, so we can split this into 3 there and 3 there, and in total there we have 9 squares. Okay, so another way of writing this was to say that c squared, just trying to change the colours so that we keep consistency here, 5 squared is equal to a squared, which is 4 squared plus, and the last one is 3 squared. So that's to say that 25 is equal to 16 plus 9. So you can see I haven't actually proved it, but I've shown you that it works in this particular case. Now that's all very well when the length of the sides are integers, whole numbers, but there are a whole lot of areas, or a lot of triangles, right-angled triangles, where the lengths of the sides are not whole numbers. Alright, before we get to that, we want to now transpose these formulas. The original formula for Pythagoras is c squared equals a squared plus b squared. if we want to make C the subject of the formula, all we really need to do is to rewrite it as C is equal to, and C is equal to the square root of C squared, so that must equal the square root of A squared plus B squared. Now notice that square root sign goes over both A squared plus B squared. That means there's an implied bracket around A squared plus B squared. It means that needs to be evaluated before you can find the square root to find C. So the formula now becomes for C is equal to the square root of A squared plus B squared. So that's transposing Pythagoras' theorem to rewrite it with C as the subject. But what if we wanted to make A the subject of the formula? So we begin with the original formula again. And you can see that you've got A squared on the right hand side, but to A you're adding B squared. And we want to isolate A, so if we subtract B squared from both sides, so we've done exactly the same thing to both sides. We have subtracted B squared, and on the right hand side B squared will disappear, so we're left with, and I'll write it up here, A squared is equal to C squared minus B squared. And of course A is equal, or the square root of A squared is equal to A, which equals the square root of C squared minus B squared. To undo square, it's find the square root of. Okay, now we're just going to finish off by applying Pythagoras' formula to a couple of right-angled triangles. And in this first one we want to find the length of the hypotenuse, that's the side opposite the right angle. Remember we called the right angle big C, and the side that's opposite its length is little c. We'll call the other sides A, so this becomes little a, and this is big B in this corner, so this side is little b, that is, I'll make that a little b. Okay, the formula is c squared equals a squared plus b squared, so we can substitute into that formula quite quickly. A is equal to 5 metres, so that's 5 squared. B is equal to 12 metres, so b squared is 12 squared. So it's 5 plus 144, and, oh, not 5, it's 25, isn't it? 25 plus 144, that gives us 169. Now let's go to the calculator and I'll show you where you can find your squared. So if we turn our calculator on, 5, there's a squared button there, and you'll see in blue we've got the square root, so it's in the second functions, plus 12 all squared, that gives us 169, which we've already found. Now we know that c is going to be the square root of 169. So now we're going to take that value, which is 169, second function square root sign, and instead of typing in 169, I'm going to select 169 as the last input of the calc, or the last calculation of the calculator. Go to second function answer, and it basically takes that 169 and plugs it in there without you having to type it in. That's really a good thing to do, especially if you've got very large numbers or very complicated numbers that you want to input into a new calculation. Press enter and we've got an answer of 13. So in context it's 13 metres, the length of the hypotenuse is 13 metres. In the last one, the unknown side, let's see, we've got side B equal to 12, so this is B equal to 12. No units in this one, notice, so you won't need any units in your answer. C is equal to 22. And remember, C is the side that's opposite the right angle. So we're looking for A. Okay. Now we transposed the formula before. We know that a squared equals c squared minus b squared. So we can now substitute in c, that's 22 squared, subtract 12 squared. So let's try this out. So this is 22 squared. Whoops, that's a bit too much, isn't it? Let's clear all of that. 22 squared plus, no, it's minus 12 squared, and we've got an answer of 340. Now remember, that's a squared, it's not a, so to find a, it's the square root of 340, and again exactly the same way as before, second function, square root. Now the second function's in blue. Second function answer takes the 340, plugs it in, and you'll notice we get a number now, and it's not a whole number. Okay, it's not an integer. So we'd give an answer there, probably correct to 4 figures, 4 significant figures, so possibly 18.44. Now we don't have a set of units, so I don't need to worry about that, but a is equal to 18.44. Sometimes you won't always get a whole number answer. In fact, there are very few triangles that will give you the whole number answers that we found with triangle 3, 4, 5 and triangle 5, 12, 13. There are some others, perhaps that's something you could research. Okay, that's the end of week 8, and look forward to seeing you in week 9. Bye for now.